In order to study trig substitutions, we need to remember some formulas from trigonometry, the double and half angle formulas. So let's start by reviewing those. First of all, for sine 2 theta is equal to 2 sine theta cosine theta. Cosine 2 theta is equal to cosine squared theta minus sine squared theta. And because of the Pythagorean identities, we can convert sine squared into 1 minus cosine squared, which gives 2 cosine squared theta minus 1. Or we can change cosine squared theta into 1 minus sine squared theta, and that'll give us 1 minus 2 sine squared theta. So these are three different ways of looking at the double angle formula for cosine. The last two formulas can then be flipped to give us a formula for cosine squared theta in terms of cosine 2 theta, and similarly for sine squared. So these are the half angle formulas. Sine squared theta is equal to 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine 2 theta over 2. So we'll frequently use these formulas in various different places as we move through the discussion of trigonometric substitutions. Let's start with a very simple and natural geometric problem to find the area under a semicircle using integration. So recall that a circle of radius a centered at the origin has equation x squared plus y squared equals a squared. If we solve for y, we get y is equal to the square root of a squared minus x squared. Of course, this formula just gives us the top half of the circle. If we put in a negative sign here, we'd get a function, we'd get the equation of the bottom half of the circle. So the area of the upper semicircle in this situation is the integral from minus a to a. These are the points where the circle crosses the x-axis. The integral from minus a to a, root a squared minus x squared. So the question we're going to address now is how do we do this integral using the techniques that we've learned and some new techniques. Of course, we know what the answer is. It's going to be half the area in a circle of radius a, so it should be pi a squared over 2. Let's see how to get to that number. Let's start with a simpler problem where there's no a's. Let's look at the area under a semicircle of radius 1. So this is the case, a equals 1 from the previous page. So notice that this integrand is only defined when x is between minus 1 and 1. If it has absolute value greater than 1, this of course will be the square root of a negative number. So it makes sense that we can define theta to be arcsine of x because the domain of the arcsine function is minus 1 to 1. Of course, this is the same as saying x equals sine theta, provided theta is between minus pi over 2 and pi over 2. This is the image, the range of the arcsine function, if you remember. Arcsine of minus 1 is minus pi over 2, and arcsine of 1 is pi over 2. So let's go ahead and apply this substitution. So our differential, we'll use the second version of the substitution to find the differential. dx is cosine theta d theta. And let's look at the integrand in terms of theta. Root 1 minus x squared is root 1 minus sine squared theta, which is the square root of cosine squared, which is plus or minus cosine theta. But since theta is in this range, cosine theta is always positive, so this is the correct sign. Now let's look at the actual calculation. So we want to calculate this integral. We do the substitution. What happens? First of all, we have to evaluate the substitution function at these limits here. So first of all, we calculate arcsine of minus 1. That's minus pi over 2. And then we calculate arcsine of 1. That's pi over 2. Now, what happens to the root 1 minus x squared? It becomes cosine theta, and dx becomes cosine theta d theta. So we have two cosine thetas terms, which will combine into a cosine squared theta. Now we're going to integrate this, and we're going to use the formula from the previous, or from the first slide. The formula is cosine squared theta equals cosine 2 theta plus 1 over 2. Now we can integrate this easily. The integral of cosine 2 theta over 2 is sine 2 theta over 4, and the integral of a half is theta over 2. We evaluate this between pi over 2 and minus pi over 2, being very careful to keep in the parenthesis and keep track of our negative signs. At pi over 2, we have sine pi, which is 0, so that first term becomes 0. And at pi over 2, theta over 2 is pi over 4. Then we subtract the value of this at minus pi over 2. Again, sine of 2 times minus pi over 2 is sine of minus pi, which is 0. And this term is minus pi over 4. So the two negative signs cancel out to give us a plus, and we end up with pi over 2, which of course we should have been expecting because it's 1/2 the area of a circle radius 1. Now we'll consider a slightly more general problem, the problem of finding the integral of the square root of a squared minus x squared, and this time we'll look at the antiderivative rather than just doing a definite integral. So we do a very similar substitution. This time x is between minus a and a, and so x over a varies between minus 1 and 1, so it's natural to define theta to be arcsine of a, in which case x is a sine theta when we solve this for x. And again, theta will be between minus pi over 2 and pi over 2. The differential now, dx is equal to a cosine theta d theta. And this thing here, this radical term, is root a squared minus x squared, which is root a squared minus a squared sine squared theta. We can take out the a squared as a factor, then take it out of the square root to give us a. Inside the square root, we then have again 1 minus sine squared theta, which is equal to cosine squared theta from the Pythagorean identities. So the square root of that is cosine theta. So let's look at the calculation now. It's similar to what we did last time. When we do this substitution, dx gives us an a cosine theta d theta, and the radical gives us an a cosine theta. So the a is repeated, giving us an a squared. The cosine repeats, giving us a cosine squared, theta d theta. Again, we use the the half angle formula to replace cosine squared theta by cosine 2 theta plus 1 over 2. We pull the a squared out the front. We integrate this. Again, we get sine 2 theta plus theta over 2 times a squared, plus c. Now, the problem now is that we want to re-express sine 2 theta in terms of x. Now, we could just say it's sine 2 arcsine of x over a, but that's not too helpful. What we're going to do is use that double angle formula that says that sine 2 theta is 2 sine theta cosine theta. So that'll give us a sine theta cosine theta over 2 when we cancel out a 2. So we end up with this, a squared over 2 sine theta cosine theta plus c. And now you see we can substitute back because sine theta is x over a, cosine theta is radical a squared minus x squared over a. So the a's on the bottom cancel out with the a squared on the top, just giving us x from the sine times radical a squared minus x squared, still divided by 2. The last theta term we just keep as arcsine x over a, and not forgetting the factor here of a squared over 2. So this gives us a final and somewhat surprisingly complicated answer for the integral of a squared, radical a squared minus x squared. It's 1/2 x root a squared minus x squared plus a squared over 2 arcsine x over a plus c. Let's have a look at a quick application of this, the area of an ellipse. Recall that in standard position, a general ellipse has equation x squared over a squared plus y squared over b squared equals 1. Again, like for the circle, we can solve for y, and we get y is equal to b times root 1 minus x squared over a squared, which we can rewrite as b over a times root a squared minus x squared. And this, of course, again, is the top half of the ellipse, the bottom half being the negative square root. So the area of the upper half of the ellipse is the integral from minus a to a of this function. And the area of the total ellipse will be twice this, so it'll be twice the integral from minus a to a of root a squared minus x squared. So we just throw in this formula we found on the previous slide and evaluate between minus a and a. So we get 2 times b over a times, well, when x is a, this whole term is 0, and this one is arcsine of 1, which is pi over 2. So that gives us an a squared pi over 4. Then we subtract off the analogous thing when x is minus a. Again, we get 0 here, and here we get negative a squared pi over 4. Adding this up, we get a squared pi over 2 inside the parenthesis. The 2 cancels out, the a cancels out with one of the powers of a, leaving us with ab pi. So this is a much less well-known formula than the formula for the area of the circle, but you see that it is a generalization of that classic formula pi r squared, because an ellipse is a circle when b is equal to a, when these two things have the same value. In that case, when b is equal to a, we get pi a squared for the area of a circle of radius a. So a very nice and neat generalization of that very well-known formula. Let's finish up this introduction to trig substitutions with another interesting problem, the integral of root 4 minus x squared over x squared. So again, we're in the same kind of general situation. We'll make the same substitution, except here now a is a more explicit number, it's 2. So we make theta equals arcsine x over 2 and x equal to 2 sine theta. Again, dx is 2 cosine theta d theta, and root 4 minus x squared is going to be 2 cosine theta in a similar way as we've seen it before a couple of times now. So the integral is what? Well, the dx becomes 2 cosine theta d theta. The radical becomes 2 cosine theta d theta. So those two things combined give us a 4 cosine squared theta d theta. And on the bottom, we have an x squared, which is 4 sine squared theta. So this whole thing becomes cotangent squared theta. To integrate cotangent squared theta, we use a Pythagorean identity to write that as cosecant squared theta minus 1. And then by a standard integral, the integral of cosecant squared is just negative cotangent, and the integral of theta is minus theta. So we end up with minus cosine theta over sine theta minus theta. And we substitute back using these two formulas. Cosine theta is radical 4 minus x squared over 2. And sine theta is x over 2. So the two 2's cancel out, making minus cosine theta over sine theta into negative root 4 minus x squared over x. And then we wrap up by just substituting theta is arcsine x over 2. So we get minus root 4 minus x squared over x minus arcsine x over 2 plus c. So this example is typical of problems that you will get when you try to integrate functions involving a root a squared minus x squared, you'll use this substitution to convert the integral into a trigonometric integral involving theta, and then you'll have to use the techniques of trigonometric integration to integrate that. And finally, you'll use this kind of method to substitute back to find the answer in terms of x.